In this video, I'll go over the answers to the multiple choice questions on the practice test. The periodic table permits properties to be predicted before the element's discovered. We know that the valence electrons really determine a lot of the chemical properties, and that we know that when an element falls below another, it should be pretty similar. So that's what the true answer is. Definitely not going to be completed with 118. Little use, that's not right, and was not completed. In fact, we're still synthesizing elements with nuclear reactions today. Argon, krypton, and xenon are noble gases that we asked you to know the different regions of the periodic table. Periodic law states that the properties are periodic functions of their atomic numbers. What determines the position? The atomic number is the number of protons. Okay, so we arrange the elements in increasing atomic number, and then we put elements with similar electron configurations below one another, similar number of valence electrons. Elements in a group or column in the periodic table can be expected to have similar properties. The atomic number of lithium, the first element in group 1, is 3. The atomic number of the second element in this group, that's sodium, that's 11. Okay, let's go on to the next page. Refer to this figure below. What do fluorine and chlorine belong to? Fluorine and chlorine are in the halogens. I didn't copy the choices, but you would choose halogens. This is noble gases. This is alkaline earth metals. And group 1 are the alkali metals. And we don't consider hydrogen to be part of the alkali metals because it behaves differently to them. Okay. Next question. Okay. Horizontal row is called a period. So remember, periods are this way, and groups are this way. Okay. The electron configuration of cesium is xenon 6s1. What period is cesium in? If you look at the periodic table, you'll see it's in the 6th row, so it's in period 6. 9 elements with in which D sublevel is being filled have the property of being metals. Okay, D being filled, that means they're transition metals, right? Partially filled d orbitals are transition metals. So if you're filling electrons into the d level, say if you were filling electrons into the 3D, then you know their outermost electrons are in the 3D. That means they're transition metals. You're in that region of the table. Okay. I think hopefully you get the picture. They're transition metals, the D block transition metals. Within the P block, the elements at the top of the table compared with those at the bottom, definitely not larger radii. We know the radius increases at the bottom. B are more metallic. No, that's not true. In fact, metallic character increases as you go down because the elements get bigger and more likely to lose electrons rather than share. So have lower ionization energies. That's not true either, because we know that ionization energy increases at the top of the group. It's harder to remove an electron from an atom at the top of the group. So the answer is less metallic, right? So oxygen is less metallic than the element at the bottom of group 6. And we know that, for example, in the carbon group, We go from carbon, which is a nonmetal, to silicon, which is a metalloid, um, to germanium. And at the bottom of the carbon group is lead, which is definitely a metal. So metallic character increases down a group, and it decreases at the top of the group. Okay, the electron configurations of noble gases from neon to radon in the periodic table make these elements part of the p block. Okay, right? They're p block. You're filling p electrons. They're in the p block. Hydrogen is placed separately from other elements in the periodic table because it, well, let's read these. Is a gas. It's true. I don't necessarily think that's why it's separate from the other ones. It does not exist as a free element in nature. That's not why it's separate. It has atomic number 1. That's not why it's separate. It has many unique properties. That's why. Okay, because we tend to group them by similar properties. So that's why hydrogen is by its lonesome. It doesn't behave like an alkali metal. It doesn't behave like a halogen. Can't put it next to helium. Can't put it really, you kind of separate from the alkali metals. All right, 13. To which do the actinide elements belong? Remember, the actinides are at the bottom. They're in the F block. Strontium highest occupied energy level is 5s2. To what group does strontium belong to? It's in the alkaline earth metals. It's in group 2. Beryllium's up here. Strontium is down here, right above barium. It's in group 2. In nature, alkali metals occur as compounds. Remember, those things are very reactive. They lose electrons very readily to oxygen in air, or if they hit any moisture, they will lose electrons, releasing hydrogen gas, and they'll become their ions. So they're more commonly found as compounds. You don't find a hunk of sodium metal in the ground. 16. The group of soft silvery reactive metals, all of which have one electron in an s orbital, is known as the alkali metals, right? One electron in an s orbital. That means these are s1. Okay, so helium 2s1 is lithium, and neon 3s1 is sodium, and potassium has 4s1, and so on. The most characteristic property of the noble gases is that they, well, not that they have low boiling points, but really the most characteristic property is that they are largely unreactive, and that's because they have an octet, and 8 valence electrons is really stable, and so they tend to not lose, gain, or share electrons at all. When determining the size of an atom by measuring the distance between bonded, identical, adjacent nuclei, the radius of an atom is, we defined it as 1/2 the distance between two nuclei. So we defined atomic radius as, here's an atom, here is another atom, here's the nucleus to one atom, here's the nucleus to another atom. And we said that half the distance, like from here to here, would be the atomic radius. Okay? All right. When an electron is added to a neutral atom, energy can be absorbed or released. So this is electron affinity. So if I do M, like an element, gas, and I add an electron to it to make an M- ion, gas, okay, energy can be either released or absorbed. Most cases, energy is released, but in some cases, like in group 2, energy is absorbed. It's required. The noble gases resist gaining an electron. Those would be required. You'd have to absorb, add a lot of energy. Energy would not be released. But many of the elements, when they gain an electron, they will release heat, and this is electron affinity. Remember, that's very different to ionization energy, which always costs energy. So it always costs energy to remove an electron. You always have to put energy in to take an electron away. But adding an electron can either release energy or it can require energy. Okay. Next one. Okay. Which represents a neutral atom acquiring an electron in a process where energy is released. So the neutral atom is A, and it's acquiring an electron. So that rules out D, because that's losing an electron. So A is gaining in A. In choice A, the element A gains an electron, but it also requires energy. It's gaining energy. In choice B, A is gaining an electron, but we never write minus energy. That makes no sense. Okay, so here, choice C is the best choice. A gains an electron, and in the process becomes an A minus ion, and energy is given off. Okay, all right. The energy required to remove an electron, that is the definition of ionization energy. Okay. 22. When an electron is acquired by a neutral atom, so this is the same process in number 20, that's called electron affinity. Okay, it's the reverse process. So this is electron affinity. Whereas 20, ionization energy is M gas becomes M plus gas, and an electron's given off. So we have to put energy in. So usually, if you're gonna write energy, you'd write it in here, or you would say that the change in energy for the whole process is greater than 0 because you have to put energy in. Positive energy means endothermic. Negative energy is exothermic. Okay, the element with the greatest electronegativity is fluorine. Remember, electronegativity is a measure of how much an atom competes for electrons when it's bonded to another atom. So when fluorine is the smallest element that actually bonds to other atoms, other than hydrogen, and so fluorine tends to attract electrons to its nucleus, or to attract electrons to it more than any other element. So when you bond fluorine to other atoms, it tends to rip electrons off them if they're metals, or if they're nonmetals, it pulls electrons toward it, making an uneven sharing situation. So fluorine is the most electronegative element on the table. Remember, electronegativity, the trend is it increases this way on a period, and that's because nuclear charge is increasing. And then it increases this way in a group because the atom size is smaller, so it's easier for the nucleus to attract electrons to it, so it increases this way. Okay. Within a group of elements, as the atomic number increases, the atomic radius, it decreases pretty regularly. Okay? Right, within a group, read the question, Mr. Randall, within a group of elements, as the atomic number increases, the atomic radius increases. So a group, within a group of elements, atomic radius increases because electrons, valence electrons, are in a higher n. So they're further from the nucleus, and there's more inner core electrons. There's more shielding of the valence electrons, so the radius increases within a group. So read the question carefully. Moral of the story. All right. In the alkaline earth metals, atoms with the smallest radii are most reactive. No, in your lab you saw calcium was more active than magnesium. Have the largest volume? No. Are all gases? No. Have the highest ionization energy? Yes. That means it's harder to remove an electron from beryllium. Like, remember, ionization energy is how much energy it takes to remove an electron. And it's harder to remove an electron from the smaller atoms. You have to put more energy to do that than you do for this process, because strontium is bigger. It's another group 2 element. And its valence electrons further from the nucleus, and so it's easier to remove. So the higher ionization energy, remember, ionization energy increases this way, and it increases this way. Okay? All right. The ionization energy for successive electrons from sodium are 496, 4,562 kilojoules per mole, 6,912 kilojoules per mole, and 9,544 kilojoules per mole. The great jump in ionization energy after the first electron removes indicates that the noble gas configuration has been reached. So it's always, you get a huge jump when you're taking that electron out of an ion that has a noble gas configuration. So remember, sodium is 1s2, 2s2, 2p6, 3s1. The first electron doesn't take much. So Na plus, I have to put 496 kilojoules to take this 3s electron away from sodium and make it Na plus. It's not a lot of energy that I have to put in, 2p6. So, but then I have to add 4,562 kilojoules to take one of these p electrons off and make Na2 plus. Okay? Na2 plus is 1s2, 2s2, 2p5. That required a lot. So the second ionization energy, the first is way more than the first because you're taking away from the noble gas configuration. Which is the best reason that the atomic radius generally increases with the atomic number in each group. So as the atomic number goes up, down a group, why does the radius get bigger? The nuclear charge increases. That's true, but it's not a good reason for the radius getting bigger. That'd be a reason that the radius would get smaller. The number of neutrons increases. Has nothing to do with the radius. The number of occupied energy levels increases. Yes. Okay, that means that you are in a higher N, further from the nucleus. Okay? A new octet forms. That makes no sense. As you move down group 14, so you're in the carbon group, from carbon through lead, the atomic radii generally increase. Same trend. Okay. As you move right in period 4, from gallium through bromine, so now you're talking about this way. Ooh, that was not good. There we go. Pieces. Ooh. There we go. Sorry. As you move left to right in period 4 from gallium through bromine, so you're doing this, atomic radii generally decrease. And then the valence electrons in group 17 has 7 valence electrons. And then for groups 13 through 18, the number of valence electrons is equal to the group number minus 10. So group 17 has 7, group 16 has 6 valence electrons. The first electrons to be removed from D block elements to form ions are S electrons. Remember, so if we take manganese, for example, it's argon 4s2, 3d5. If we make a manganese plus 2 ion, it loses these electrons, these 4s electrons first, because those are in the highest N, argon 3d5. Okay, so you lose the s electrons first. Okay, and that is it. Hopefully that helps.